That's so weird.
Does every lecture start with somebody laughing?
I think so. I think so. There's this pause, like, I don't know. Or maybe I just turned the camera on in a absolutely hilarious way. No seat for you! No seat for you! No one thought to get more than one chair. We all just were like, me! I'm just getting a chair for me!
I was worried about
Full over. Okay. All right. So today we have to slog through the trenches of calculations. And if you can survive and still have paper left in your notebook, I promise that next week will be a considerably more interesting set of topics. But we just kind of have to talk about calculations today with the weak interactions because they are obviously they're very significant because anything that can decay has to decay through the weak interactions. For economy of time and as a quick reminder, this is essentially where we have gotten to in our development of the Feynman rules for all of the forces. So very quickly, although not part of the standard model, the simple ABC theory was a good place to start because it let us get some idea of what the Feynman calculus looks like without all the complications that clearly eventually ensued. The first force we studied was QED, and so the essential ingredients to remember, you draw the diagrams based on the allowed vertices, and the allowed vertices are actually all the way over here. And then you use the diagram to start writing down a set of factors, and there's a set of rules, that you kind of follow. But every external label in QED, if it's a spinner, a piece of matter, it gets a U, a U bar, a V, or a V bar. If you have an external photon for your diagram, which we didn't actually work any diagrams with external photons, then you would write down polarization factors for the photons. Remember, these external labels are just labels of the spin state. The motion, the momentum, and the energy, all of that is going to be taken care of in the golden rule. Okay? So we're really just interested in labeling the spin properties. If you've got internal matter, you put down a propagator of this form. And then if you have an internal photon, which we typically do, if there's an interaction, then you have an internal propagator for the photon of that form. And then we know that all of QED is built off of this basic vertex where a charged particle comes in, the photon leaves, and the same charged particle leaves the vertex. And then we write down a vertex factor that involves a gamma matrix, which is one level of complexity. We're going to have to deal with spinors and spin matrices. Now, very quickly, in QCD, the one new ingredient on the external labels was that all of the matter fields, and notice these are quarks now, because we wouldn't be doing QCD with leptons. Leptons don't feel the strong interaction. But in labeling the external states, we don't just have to say what their spin state is, but also what their color state is. So that's what the C's and the C daggers are telling. And then we also have sort of a gluon label, a gluon color assignment for external gluons, should we have external gluons in a diagram. And then we also, of course, have to give them polarization vectors, just like we did for the photons. So I'm trying to draw your eye to the similarities between the labelings here and the differences. Gluons carry color, they're bicolored, so they have to have these A labels. The photon doesn't carry any charge, so it doesn't have an extra label. You just have to tell me what its polarization is. Internal matter, same story here. Internal gluons, the only difference is we have this delta function on the alpha beta labels that you would be putting in for matter lines. Or for gluon lines. This delta alpha beta is actually going to typically contract for vertex factors. So one of the other new ingredients with the strong interactions is that we get not just the basic vertex, which itself carries a new component, lambda, but we also get gluon-gluon interactions, and they're so bad I don't even write them down. Okay, you can go look them up if you really want. They should be on that sheet that I gave you. And then overall, unless you're taking these kinds of diagrams with these into account, which get nasty, if you just think about QCD diagrams with these kinds of vertices, evaluating QCD diagrams is really not that much worse than evaluating QED diagrams. In fact, the only difference that you encounter is that for a QCD diagram, you typically have what factor that you have to evaluate?
Color factor.
A color factor, right. So there's some overall thing that you can actually shift out of the whole calculation and just say, what's the color factor? And you can evaluate it given the color states, and it's going to be a number. So really and truthfully, QCD, as long as you don't deal with this, is not that bad. Not so for the weak interactions, which you notice takes up about 50% of the real estate on the board, just to get the bits across. So external state labels, good news, they look a lot like QED. Okay, there's no color that we have to label. Unfortunately, there is, despite the seeming similarity, there is a subtle difference, and that is that when you're labeling external weak boson states, so when you're given polarization vectors for the weak bosons that are external to a diagram, these have 3 polarization states. As opposed to, in the case of the photons and the gluons, there were 2. Why, Andrew? Andrews. Brad. Hi. Brad. Using a meme, if you can, explain to me why we would have 3 polarization states for the weak bosons external to a graph, but we would only have 2 polarization states for gluons or photons. Why 3 versus 2? So these are all vector particles. They all have a space-time vector index. So if you will, they're spin 1 particles. But I'm somehow saying that these have 3 states and these have 2 states. What other difference in these can I kind of tie that to?
Are you getting at half integer spin, or?
No, they all have the same spin. They all have spin 1. Matt?
They're massive.
Yeah, so the difference is that gluons and the photon are massless. So when we classify their spins, we cannot go to their rest frame. We have to just pick a sort of a vector along the direction of their motion, and then we classify their spin by the symmetries perpendicular to that. So that's a 2-dimensional plane if you're perpendicular to a vector. And so you only get 2 spin states. But since the weak bosons are massive, we classify their spin states according to their rest frame, and in their rest frame you have 3 dimensions that you can rotate with respect to, and so a spin 1 particle in 3 dimensions has 3 states. So that's the key difference between the gluons, the photon, and then these weak bosons. If I have internal matter lines, same factor. In fact, you kind of could have expected this, because for an internal propagator of a piece of matter, the internal propagator is only describing the motion of the thing through space-time. There's no interaction. So that is always going to be governed by the Dirac equation, essentially, because these are all spin-1/2 particles. So the fact that you keep seeing the same internal propagator in all these theories is just a reflection of the fact that the propagator is just governed by the Dirac equation. Okay? The interaction terms are where the differences pop in. Okay, so if we have an internal propagator for a weak boson, and when I say internal, what I mean is this is an internal propagator. Okay? It begins and ends completely within the diagram. The propagator for an internal boson looks like this, and you'll notice something immediately about the connection between this. And what is that? Matt?
Same thing with n equals 0.
No, it's not. But that was a very good guess. It's what you would expect, right? You would think that if this is the propagator for a massive particle, and this is the propagator for a massless particle, then if I take m equals to 0, this should reduce to this. But you'll notice that it doesn't because of this term right here. The m is in the denominator. So by the way, if this is not clear, this is the metric. This is the q, the 4 momentum of the internal particle. That's the same thing that's squared here. This is q mu, q nu over mc, where m is the mass of the mediator, and then over the usual q squared minus m squared c squared. Okay? So what you notice is that this doesn't have a limit to the massless form. Does that bother you?
We derived it.
Say it again?
Didn't we derive it in a different class? Or like earlier this semester?
Didn't we derive this?
Or we showed that there was an equation that sorts to both of them, and you can cancel out the M earlier, and then it doesn't propagate through to now the divide ends.
Yeah, we actually studied the massive Proca equation, and then we got the propagator from it, and then what we argued was that in the massless case, you actually have to go back and you have to apply a gauge condition to derive the propagator. Rochelle?
Oh, I was going to say, like, it wasn't continuous when we looked at it.
Exactly, that's exactly what I was about to say. This is not a continuous limit. You would think that going from massive to massless is continuous. You just dial the mass to get really, really small. But we just pointed out that something discontinuous happens. You pick up an extra polarization state. That's a discrete change. So the fact that this isn't a continuous limit is okay. Okay, all right? Okay, and then, so external factors, internal propagators, the weak interaction vertices. If we're acting on leptons, if we have charged weak interaction bosons coming out of the vertex, then we use this factor. That's reasonably straightforward. However, if we have a neutral weak boson, the Z0 boson coming out, we use this factor where unfortunately these coefficients CV and CA are different for elements of different families according to this chart. Okay, so it makes things a little hairier. And then if we're dealing with the charged interactions of, and by the way, I should point out, this is the rule for leptons. This is the rule for anything. It can be a lepton or a quark. Okay, the Z0 couples to leptons and quarks in kind of the same way modulo these changes. However, if we're doing the charged bosons coupled to quarks, then we have to bring in elements of the CKM matrix. Okay, so when you're writing down the vertex factor for a vertex where you have a quark coming in and a quark going out, then you have to include, in addition to all the usual stuff you see here, the CKM matrix element, which connects the quark coming in and the quark going out. And what I have in mind here, high and low, is a upper part of the doublet or a lower part of the doublet. Okay? So you know, just the weak interactions are complicated. And why are they complicated? Jonathan? Why are they complicated?
Not gonna lie, I was zoned out for like 5 minutes.
I like the honesty. Jacob's not here. I'm just going to go through. Jacob, why are they complicated? Why are they so much worse than like the strong interactions? We talked about this last time, like the weak interactions are ugly because it starts with a T and it rhymes with the symmetry is broken. Okay, good. Yes, the symmetry of the weak interactions is broken at ordinary temperatures, and so we've got that whole Higgs effect and a really nasty looking Lagrangian that comes out of it. And generally we would expect that to make the Lagrangian more complicated, hence the Feynman rules that come from the Lagrangian more complicated. Okay?
But I don't know what you call it, but the electronic interaction or whatever, I don't know what you call it, but that's not broken?
The electromagnetic?
Sorry, yeah.
No, so that's the interesting thing. When you break the weak interaction, so the electroweak interaction is where you start. It's based on SU2 left cross U1 hypercharge. It has 4 generators. And when you break it, you actually break 3 parts of it and you leave 1 unbroken. And the fact that one of them is left unbroken, which is what ends up being electromagnetism, is why that part of the story still looks nice and pretty. I want you to remember, it's not just that you have 4 things and 3 of them get broken. It's combinations of things that get broken and not, so it's a little more complicated than that. Okay, so the good news is that I added a problem to your homework.
Oh. Woo!
And you are going to get to calculate a process using a diagram that uses QED, QCD, and the weak interactions.
Wow.
And you're going to get to see these complications. Now, it's a relatively long calculation, so I wouldn't wait till the last minute to start on it. Okay, it's the only problem I'm going to add. So you've got 3 problems for your homework, but start on it early and think and work efficiently. because you don't need to repeat a lot of stuff. For example, if you do the QED calculation and then you go to the QCD calculation, don't repeat everything from scratch, because we already alluded to what the difference is. And when you get to the weak interaction part, which is the really new thing because you haven't done anything with it, it's going to seem really ugly. So just take care and be thoughtful and organize your work, and it's not going to be as bad as you think, okay? But you're going to get experience with all three of these before this class ends. All right, so I'm going to do some sample calculations today, but before I get started, I want to talk a little bit about this factor that seems to be appearing in all of the weak interaction element vertex factors, and that is basically this structure gamma mu minus 1, gamma mu times 1 minus gamma 5. Okay? Just want to say a couple words about this because it obviously appears here, it appears here, and then it kind of appears here. Okay? So what is going on with this particular factor? Well, let's recall for a moment, we talked about this when we talked about the baryon asymmetry of the universe, that one discrete symmetry of nature that is interesting to consider is the operation of parity. And we can think of the action of parity as a reversal of an odd number of coordinates. So if I act on, if I act on x, y, and z with a parity operator, I'm just going to get minus x, minus y, minus z. Okay? It has to be an odd number of coordinates because if I reverse an even number of coordinates, then Colton.
You dropped the class in the wrong.
Rochelle. You know your pictures all look so up I can't figure out, like, you guys are driving me nuts. Rochelle, why is it problematic to think of a parity transformation acting only on 2 coordinates instead of an odd number?
Because
Or an even number versus
have a
none?
problem with it still being SU or something? Like because the determinant wouldn't be able to be 1?
So mathematically speaking, that is the root of the problem. But in more qualitative terms, if I do an inversion of x and y, I can also realize that as a rotation. So I want parity to be something different from rotations. And so in order to get that, I always have to be reflecting an odd number of coordinates. Okay? So this is the action of parity on the coordinates. And then if you dig into the definitions of spinors and how spinors transform, let me put Jacob's card back on top and leave it there. There we go. Okay. Snooze, you lose. So if we actually look at the definitions of spinors, Dirac spinors, and how they transform under coordinate transformations, which we did earlier in the course, we wrote down the generators of the Lorentz group, and we showed how they act on spinors. Then what you eventually discover is that parity acting on a Dirac spinor is equivalent to gamma 0 acting on the Dirac spinor. So the gamma 0 matrix actually corresponds to the parity operator on a Dirac spinor. Now we can immediately get some interesting conclusions out of this. So this tells us, for example, that if I consider the simplest spinor sandwich, psi bar psi, then if I do a parity transformation on it, it's going to transform into some new object. And so I can think about, so if the notation's confusing to you, sometimes we write it like this. Psi goes to psi prime, where psi prime is gamma 0 psi. Okay? So let's explore what parity does to this spinor sandwich. So I'm gonna do a parity transformation of each of these, and that of course means that I'm doing gamma 0 psi bar, gamma 0 psi. But if I remember the definition of barred is by definition the thing that's being barred daggered times gamma 0 daggered, times gamma 0. So psi bar is psi dagger gamma 0. So I'm just taking the bar and breaking it up here, and then again I have this, that's got a lot of stuff going on here. This is this guy right here. This gamma 0 comes from undoing the bar, and then I still have this term. So now I can do the transpose dance without Hermitian conjugation. And Jacob is going to remind us of the useful property of the gammas. Gamma 0 squared is?
Gamma 0 squared.
Is?
Gamma 0 squared.
Is?
Gamma 0 squared.
So that's a triviality. I want a non-trivial answer. Nathan? Yeah, I thought he was going to ask a question, but in fact he was giving me the answer. This is just the identity. Okay, so psi dagger, and then we have this really nice result that gamma 0 transpose is actually the same as gamma 0. And at the end of the day, oh look, it's Jacob. Jacob, what is that equal to?
Your mom.
Excuse me? We're not going to ever say that again for a host of reasons. Many, many reasons. Jonathan. Oh, Joe, you want to answer it?
Side bar side.
Yeah, it's psi bar psi. Okay. So at the end of the day, the simplest spinor sandwich psi bar psi is invariant under parity. Okay, so that's invariant, and we typically call that a scalar. Okay. So now what I want to do is I want to consider a slightly different object, and that is psi bar gamma 5 psi. Okay. And if I do a parity transformation on this, most of what I just did here is going to play out. Okay. The only difference is that these two gamma zeros right here, which I eventually replaced by the identity here, they're going to have a gamma 5 between them. Okay, so at the end of the day, I can write something like this. But remember, gamma 0 dagger is just gamma 0, and that's a gamma 0, so that's the identity. And so at the end of the day, this is psi dagger gamma 5 gamma 0 psi. And then I would like to take the gamma 0 and combine it with the psi dagger to make psi bar something, but I got to get that gamma 0 past gamma 5. Can anyone remind me of a useful property of things moving past gamma 5? They always pick up a minus sign. So when I move the gamma 0 past the gamma 5, I pick up a minus sign, and now I can recollapse this to psi bar. And so it turns out that the combination psi bar gamma 5 psi picks up a minus sign under parity. So what kind of object is this? It is what is called a pseudo scalar. It is a scalar. It has no space-time vector index. So under rotations, it transforms just like a scalar. It's invariant. But under parity, it picks up a minus sign. Okay? Now, it might not surprise you that if I take this combination, instead of the simplest spinor sandwich, consider this spinor sandwich with a gamma matrix in here, then this thing will transform into minus psi bar gamma mu psi, which tells us that this is what kind of object?
Pseudo vector. Pseudo scalar.
It's a regular vector. Okay, let me just walk you through this. It's got a gamma mu, so I kind of see there's a vector index, so I want to use the word vector. But remember, vectors change sign if you flip all the coordinates. So normal scalars don't change sign, but vectors do change sign. So this is what you would expect for a vector. Okay? It might not surprise you, though, that if I throw a gamma 5 in here, and I transform that, then I actually pick up an extra minus sign, and so this thing becomes itself, which is the behavior of a pseudo or axial vector. Okay? Now, why am I going through all this? Well, I'm going through all this because when we construct weak interaction Feynman diagrams, we're going to encounter spinors barred with gamma mu 1 minus gamma 5 times some spinor. But of course, this is just going to be u bar gamma mu u minus u bar gamma mu gamma 5 u. U's are just their size, their particular size. So the first term in that is what kind of quantity? It's a vector. Second term? Pseudo-vector. I'm going to call it an axial vector. Okay. You might have noticed this kind of mysterious V and A label right here. That's actually what this is labeling. The term with just gamma mu is what we call the vector part of the coupling. The term with the gamma 5 is what we call the axial part of the coupling. Okay? And then there's, of course, a minus sign in here. Now, what is the significance of a vector minus an axial vector in our coupling?
Under transformation, they add.
Under the transformation, they
switch.
So you're both saying something very important. Finish the thought. What happens?
If the whole thing becomes negative?
Yeah.
Or wait, no, the whole thing becomes a negative half.
What does that become?
A minus B.
It becomes minus v minus a.
Dang.
Remember, the axial vector doesn't change sign. Okay? Now, why is that significant?
The axial part doesn't change.
Say it again.
It's neither axial nor a vector.
It's not axial. It's not a vector. Why is it important that I have the difference of two things and those two things are transforming differently?
Because differences are usually
Well, the axial part is invariance. The axial part has some sort of physical meaning on its own, and the vector part has some different, like they correspond to different things, right?
They definitely correspond to different things, but what is so let us suppose that we were calculating a diagram, and from the calculation here I got, you know, the number 2. And from the calculation here I got the number 3. So these two would combine to give me minus 1. If I took the exact same process and I considered the parity reflected version of it, I would get minus 2, minus 3, which is minus 5. I would get a different answer.
Yeah.
So what is this V minus A term providing for the weak interactions? Parity violation. But we've already talked about that. When we talked about the baryon asymmetry of the universe, we observed that the weak interactions violate parity. In fact, they violate parity maximally. And it's exactly in this gamma mu 1 minus gamma 5 term that appears everywhere that is the source of the parity violation. Okay? Now, parity violation is very interesting. It was a complete surprise when it was discovered in 1964. People up to that point figured all of physics was parity invariant. But what became truly impressive was when they later discovered CP violation. And then CP violation is actually where you have to dig into the guts of the CKM story. So we're not going to bother with that today. I just wanted to point out the sort of ubiquitous role of this gamma mu 1 minus gamma 5 everywhere and what it does to the weak interactions. Okay. All right, so now we're going to get into the guts of some calculations. And so some of these weak interaction expressions are going to be useful to reference at some point, so keep those in sight. And by the way, you're all have you encountered pseudovectors before? Oh, okay. All right. So the simplest example of a pseudovector is the cross product of two vectors.
There was like an arbitrary choice, which
Because if I do the parity transformation of a product of two vectors, each of these vectors picks up a minus sign, but the whole thing therefore picks up a plus.
Yeah.
Okay.
That's just a normal vector.
Say it again.
That's just a normal vector.
That's not, no, a normal vector picks up an overall minus sign.
Yeah, but okay.
So you get used to saying things like this, G is R cross P, and saying this is a vector, but you should not be saying that. This is a pseudovector. Okay, if it were a vector, it would pick up a minus sign under parity, and it doesn't. Now that leads to an interesting puzzle. Anybody seen that before?
all
Yeah.
I think so.
Yeah, where's that come from? Yeah, that's Lorentz force. This is the interaction term for electromagnetism. What is this? What kind of quantity is that?
Vector.
That's a vector. What kind of quantity is that? It's a pseudo vector.
Parity violation?
Well, why didn't we talk about parity violation in the electromagnetic interaction?
Because everything, like we had right-hand rules to describe all the pseudo vectors for positive charges, and then negative charges just behave oppositely, right?
It's a good guess, but no. I mean, it's a good guess.
It works.
I mean, based on the argument that I just made, and the fact that this is a minus and this is a plus is irrelevant. If I do parity on this, it becomes, which suffers the same problem.
It's because we're working with potentials, like B fields and B fields.
And what about that is important? That's a key element of this.
It's like the Hall effect.
Potentials are directions, or
Is this not just a manifestation of the Hall effect?
Does it have to do with the fact that it's relative? I think they're actually four-dimensional.
What kind of quantity is that? Pseudo vector. The B field is the pseudo vector. How do you get the B field from a vector potential? You take the cross product. So this is a vector across the pseudo vector,
Which is a vector.
which is a vector. Okay. So the electromagnetic interaction, I mean, you got to be a little bit careful, right, when you play the sign games. All right. So the electromagnetic interactions they can serve parity. All right. The weak interactions, though, definitely break them. Okay. So, all right. So let's get into the weeds with some calculations, and we'll start with perhaps the simplest and perhaps most relevant calculation with the weak interactions, and that is the decay of a muon. So the muon is the second lightest of the massive leptons, and it's not the lightest, the electron is. And so as we tend to expect, heavy particles decay to lighter particles when they can. And so the muon is going to decay. It's going to decay into an electron plus some other garbage that will kind of take up conservation of various things. And what we want to do is we want to calculate the amplitude for this, and then from that extract the lifetime of the muon, or an estimation of the lifetime of the muon. Now, we're at the point where I'm not in any way, shape, or form going to be able to go through every single step in the calculation. But I'm going to try and show you some of the more salient parts. So let's start with a diagram of this process. So we can have a muon coming in with some momentum P1, and then we'll have a vertex and the muon neutrino coming out with some momentum 3. And then this is going to occur via a weak interaction, of course, a charged weak interaction. And then there'll be a vertex up here with the electron coming out and the anti-electron neutrino coming out as well. And then I'm going to just, for labeling purposes, call this momentum 4 and call this momentum 2. Okay, so 1, 2, 3, 4 are just momentum labels. And if you take this diagram and you apply the Feynman rules for the weak interactions, you're going to eventually get to a quantity that looks like this, where many of these elements are going to be familiar. And again, I'm skipping quite a few steps. The whole write down delta functions at both vertices and then integrate over momentum and then use a delta function to do the momentum integral. I'm just going to assume we've all done all that. It always kind of works out the same for a diagram with 2 vertices. It's always pretty straightforward. And then we're going to have this nasty looking propagator term. All right, so a lot of the ingredients of this should be familiar. You know, we're starting on the outgoing neutrino, following the line back through this vertex into the incoming muon. And then similarly here with a vertex factor, and then that's the propagator for the internal W plus or minus, depending on which way you want to draw the arrow, it doesn't matter. All right, very important observation for your homework. Pay attention. If your friend is sleeping, wake them up. If your enemy is sleeping, let them sleep. We are going to make an approximation. You don't want to evaluate this propagator if you can avoid it. It sucks. Okay? So what we're going to do is we're going to make an approximation that the momentum transferred, so the momentum transferred is just the total amount of momentum that flows through this line. Okay? It's the change in this or, you know, once you get up there. So it doesn't matter, but we're going to assume that the momentum transfer is considerably smaller than a scale set by the mass of the weak boson times the speed of light. Okay? So you can kind of think of this as a low energy process. And in that case, the good news is that this term right here is approximately 0, and I can ignore the q squared in the denominator. Okay? So in this case, my vertex factor just reduces to I eta mu nu over mw squared c squared, which is a hella lot easier to work with than the thing we started off with. Okay? Yeah?
Is that supposed to have a minus sign? Or is it?
So that minus cancels that minus.
Oh, okay. Sorry.
Okay. All right, so working in that approximation, we're going to have something left over that is going to be, cleaning everything up, g weak squared. Actually, I shouldn't say g weak. This is GW, where W is for the W plus minus boson. For the weak interactions, we have GWs and GZs, and these are related to each other through factors of sine or cosine of the Weinberg angle. So I have in mind a specific GW here, over 8 MW squared C squared U bar 3 gamma mu 1 minus gamma 5 U1 U bar 4 gamma nu 1 minus gamma 5 V2. Okay? So that's our M. Now, before I continue with this, for your homework, I'm going to actually ask you to evaluate this. And what I mean by that is I'm going to give you definite spin states. So I'm going to say, like, this particle is in the state U1, this particle is in the state U2. You can go and look up the form of these spinners. We've looked at them. Okay? When you do this homework problem, make sure you don't go back to stuff before we started doing Feynman calculus, because remember we changed conventions and I gave you all the new expressions, and if you kind of mix early expressions with new expressions, things will go sideways. But if I gave you the actual spinners to use, and remember what these look like, they're like a normalization factor times a bunch of px over e plus, you know, stuff like that.
Yeah.
And then if I also give you the 4 momentum for all the external states, like, you can literally explicitly evaluate this, and that's what you're going to do in your homework. Okay? For now, though, we're going to actually take this and do the other thing that we tend to do, and that is we say, well, I don't actually care what the spin of this is, and I'm not going to look at the spins of what comes out. So we're going to average over the incoming spin, and we're going to sum over the outgoing spins. And that's where we get to use those nice trace results for gamma matrices. And so m squared to leading order is just going to be given by, and again, there's a lot of work from going from here to here, but I'm just going to quote the result. So 1. Okay. So the form of that, you know, although not obvious, it should be vaguely familiar to you from when you actually did some of these spin averaging and sums in the homework. You know, everything ends up just being a number times a bunch of dot products of 4 momenta. Okay, you worked out examples of this in the homework, Ashley.
Why is the G changed to GE? Is it supposed to?
It was not supposed to. It's supposed to be a GW. Because I love GE. My refrigerator's GE. I love GE. I'm just kidding. Okay, all right, so you guys obviously don't find my jokes funny. I mean, that's okay, because I don't find any of you funny. So, if for simplicity we would like to look at a muon which is at rest, might as well keep it simple. Put a muon there, let it go, and then it decays. Stuff shoots out. Then the form momentum coming into this is just going to be m mu c 0 vector. And if I take this expression and I apply energy momentum conservation, I've got zero momentum, zero spatial momentum, and then I got a 3-body coming out, I can actually massage this expression for the spin averaged and spin summed square of the amplitude to the following form. And again, there's quite a bit of massaging these form momentum expressions with that explicit identification in there. Okay, and now if we want to calculate the lifetime of the muon, what would we do? Jonathan, I guess you didn't get to answer your question earlier because Joe friended you. If we want to calculate the lifetime of the muon, what would we then do with this m squared? Stuff it into what? Stuff it into whose box?
No idea.
Fermi's golden little box. Yeah, we would put in a Fermi's golden rule. Okay. Now, remember when we worked with Fermi's golden rule in the past? Okay, I gave you some expressions that were general, and then I gave you some expressions which were really nice. They were really clean, little simple expressions. What were the situations where those simple expressions were applicable, Matt?
Two-body.
Yeah, it could either be a 2-body decay, or it could be 2-body scattering in the center of mass, or in the center of momentum frame. Okay? Is this process either of those? No, it's 3-body decay. Okay? So unfortunately what that means is if you want to actually go back to Fermi's golden rule, you can't use one of those simple little forms. You have to use the whole beast. Okay? So I'm not going to wade through the details of this. There's some write-up in the notes if you're really curious about it. But in the end, it becomes a very, very nasty, you got to do a lot of integrals over form momentum, and it gets kind of ugly. But at the end of the day, you can do those integrals. And so we calculate for the lifetime of the muon, which is just 1 over the total decay rate, where right now, so remember the total decay rate is actually calculated as a sum over all the channels. So each channel is a particular set of decay products. When I want to know how long something lives, I just want to know how long it's going to be there before it's gone. So I don't care what it decays into. So I have to sum over all possible things it can decay into. Okay. The good news is that for various reasons we can argue that this is by far the most common thing this decays into. So if you calculate this guy, that's pretty much gamma. Okay, or at least it's a leading approximation. So then to get the lifetime, we just do 1 over the gamma associated with this. And we find that this is, this comes out to be mw over the mass of the muon times gw to the 4th times 12 h bar 8 pi cubed. And a lot of new factors show up here because of Fermi's golden rule. And this approximates to how do I want to say this? Yeah, okay, all right, so, well, okay, so how would we, so, okay, we can approach this in different ways. One way we can approach it is we can say, okay, I know the values of all of these things, plug them in and calculate the lifetime of the muon, okay? However, historically and experimentally, that's not the way it goes. We normally measure the lifetime of the muon. We take a collection of muons, and then we calculate how long it takes for approximately half of them to decay. We get an estimate of the lifetime of the muon from that. And so what you typically do is you measure this, and then you use that measurement to determine something in here. Okay? So one thing that you can do is you can take the lifetime of the muon, which is 2.197 times 10 to the minus 6 seconds. And what you have figured out about the mass of the W boson, which is 80,420 MeV per c squared. Okay, and you can use those as knowns and extract the weak coupling from this expression. So, you know, all of these numbers have to be measured. You got to measure the lifetime of the muon, you got to measure the weak coupling somehow, you got to measure the mass. Well, mass measurements are not that hard. We've got lots of techniques to figure out the mass of something. Lifetime measurements are not that hard. How you measure the coupling of something is a little more abstract. So why don't we treat that as the unknown? And then if we take all of this together, then we find that the weak coupling is about 0.653. All right? Which implies, if I want to write this in terms of something like the fine structure constant, which would be GW squared over 4 pi, this is 1 over 29.5. Okay? And you can compare that to alpha for the electromagnetic interactions, which is 1 over 137. Okay, so as promised, this result is reflecting the fact that the fundamental coupling of the weak interactions is actually significantly larger than the coupling of the electromagnetic interactions. All right? And Madeline is going to remind us that even though this is fundamentally stronger than this, the weak interactions are still overall weaker because yes, exactly, because the bosons that mediate the interaction are massive, and you can see exactly where that comes into play. In the amplitude M, the mass of the boson is in the denominator. It's squared. It's huge. It's hella huge. It's ginormous, as Wolfgang would say on his senior design poster. Okay? All right. So there's our first example of a calculation.
Yes.
There are lots and lots of steps I have not filled in here. Okay? But if you're curious, you know, you can go and look at the details of Fermi's golden rule. That's, you know. And I have to say, like, a lot of the quantum part of this, the Feynman part of this, is you're done with once you get here. Once you've got this expression, going into Fermi's golden rule is just a manipulation of kinematic quantities, you know, relativistic kinematic quantities. I mean, it's not, it's tedious, but it's not particularly exciting or, you know, insightful. Okay, so process number 2. We've talked about muon decay. Let's now talk about the decay of something else important that we know decays. Due to weak interactions, of course, and that would be what is perhaps one of the most significant decays that we should consider.
Free neutron?
A neutron, yeah, let's talk about neutron decay. Okay. So for neutron decay, we've got a process in mind that looks something like this. And if I drew a Feynman diagram for it, I'm going to be a little bit lazy, and I'm just going to call things neutrons and protons. And we know the reality of this story. We know that secretly these are really bound states of 3 quarks, but I'm going to see if I can get away with just neutron and proton. So if I draw the diagram for a neutron coming in and a proton coming out, and I conveniently label my momenta as so, then there's clearly a W plus or minus that's associated with this because there's a sign change in the electric charge. There's going to be a vertex up here, and I'm going to have the electron come out. I'm going to call that momentum 1, and I'm going to have the anti-electron neutrino coming out, and I'm going to call that momentum 2. Caroline. Oh, Caroline. What does that look like? Yeah, it looks pretty much exactly like the last diagram that we calculated. Joe Bales.
Don't you need to have a momentum pool instead of 2 momentum ones?
You know, I can do, I do 2 ones if I want. I roll with 12 ones if I want.
Let's be.
My life, my gang, I do what I want. All right, yeah, that should be a 4. Thanks for sucking the life out of this lecture, Joe Bell. Okay, good news. This is exactly the...
Sorry to interrupt. I wasn't able to browse your presentation and I lost my keys. Did anybody find a pair of keys?
Oh, keys in this room.
On the podium, yes. Around the podium.
So around the podium? You're welcome to come in and look around. And move my stuff
Let's try
around.
to get home.
No, that's a reasonable endeavor. What are we looking for exactly?
Mine's lanyard.
Mine's lanyard.
Did you talk to Lakshmi? She's like lost stuff.
I just talked to Lakshmi.
Oh.
She told me to ask. Or check her and ask us.
I don't see it in here. The only other thing is, if I don't know what's in that box or around and behind those tables.
You also asked Barbara.
That's my next step. I'm going upstairs.
Barbara might be gone.
Oh.
They are gone, but custodial's upstairs. Thank you,
Yeah, I
guys.
don't see them in here. If they pop up,
Appreciate your time.
we'll come screaming. Okay. So the good news is that this is exactly the same diagram that we had before, so we can skip straight to the. Oh shoot! Oh yeah, sorry. Yeah, I forgot to say something in my previous non-example, but I'll make up for it. Okay, why did I erase all that stuff? I should have just changed labels and I would not be repeating writing down stuff. This is stupid.
I didn't write it down the first time, so we
Shh. You guys are bothering me. Stop bothering me. Okay, so when I looked at the muon decay process, there was an approximation that we made, and I didn't actually point it out. But there was a point in there where there was a factor that looked like this. Okay? This was in the muon decay analysis. And then to get the actual result that I got to, because otherwise it's just that ugly, this is 105 MeV per c squared. This is 0.5 MeV per c squared, so we actually just used the mass of the muon times c squared for this term. Okay. That quantity, by the way, is essentially the energy that's released when the muon decays. Okay, because you're essentially going from a bare minimum of the rest mass energy of the muon to the rest mass energy of the electron, and all the other stuff gets to go into kinetic energy of things flying out. Okay, so in the case of neutron decay, the energy released is actually the mass of the neutron minus the mass of the proton minus the mass of the electron. And as you're probably aware, the mass of the proton and the mass of the neutron are comparable to each other. And so in this case, we're not going to be able to make an approximation like that. Okay? So that's going to make some things a little bit uglier, but in the end, we're not going to look at the details anyway, so I'm not actually going to belabor the point. If we go through the calculation with Fermi's golden rule and calculate the lifetime, now this is important because now we want to calculate tau. So we know the mass of the boson. This time we're going to say we know the coupling, GW, and then treat this as the unknown. And if we do this, we get a value that is 1,318 seconds. Okay. Now, the issue is that the observed lifetime of the free neutron is actually about 885.7 seconds. And so there's a disagreement. And you know, the first thing to observe is that at least you're in the ballpark. Because we know that with lifetimes, you know, you can get lifetimes that are 10 to the minus 6, 10 to the minus 10, you know, so at least we're order of magnitude. So we're doing something right, but we're clearly doing something wrong. Jacob.
Don't we just need more decay channels? We only considered one process.
So that's an interesting option that we could explore. And if you start exploring the other decay channels, what you actually find is that they won't change this answer significantly. Okay? I mean, they're going to change it somewhat, but they're not going to change it enough to justify this difference. Okay, so the issue that arises is the following. What observation did we make when we first drew this diagram? We're not treating these things as bound states of quarks. Okay? And where this becomes important is that if we were honest about it, and we did this, okay, the problem is that there's no sense in which we can say that this vertex definitely ties to one of these up quarks. Or, maybe it ties to this up quark, or maybe it ties to this down quark, or holy hell, what if it does this? Remember, inside of a baryon, there's a lot of gluons that are being exchanged between the quarks, and they can create virtual quark-antiquark loops. And so maybe this vertex is actually coming off of one of these virtual quarks. There is a zoo of possible resolutions of this vertex if you actually look at the quark picture. And it's really the quark-gluon picture. Okay? Well, it's going to be hopeless to actually try and calculate this because there's a gazillion different possibilities. So what we can do, and this is a very popular technique in calculating these sort of high-energy amplitudes, is we're just going to put in a factor that we call ignorance. We're going to say, I don't actually know what that vertex looks like completely. Now, that's not a total loss because there's a lot of stuff that we do know about this process. There's energy momentum conservation, there's electric charge conservation, so there's a lot of stuff that you can do. And what we can effectively tease out of this is that the normal vertex that we would put here, which would include a factor of 1 minus gamma 5, okay, that's the normal, the vertex factor normally has a 1 minus gamma 5 contribution. We can replace it by some factor that looks like this. Okay? And then we can basically put our ignorance into these two coefficients and say the coefficients here, whatever values they are, they're taking into account the fact that this is not a single, simple, weak interaction vertex. Okay? So we can calculate this using this CA and this CV. We can massage out the, we can actually do calculations for different processes using this same ansatz. So in particular, we can do this calculation for free neutrons. We can do this calculation for neutrons which are bound inside of a nucleus. And at the end of the day, what we find is that this term is approximately 1, and this term, can't draw an arrow, it's getting that late in the day, this term is approximately 1.27. Okay? So what we find is that you can do this as an effective vertex and get close to the right answer. You're just not going to use 1 minus gamma 5 where it would normally appear. You're going to use 1 minus 1.27 gamma 5. Okay. Now what's interesting about this is that this is 1. That is, this term at least is exactly the term that you would have naively thought. So all of this complicated stuff going on in here somehow does not screw up the vector part of this coupling. It does screw up the axial part, okay? And we would expect things to change, but the fact that something doesn't change is weird. And so this is associated with what is often called the conserved vector current hypothesis. That somehow there's some symmetry that is protecting this part of the coupling, despite that there's a lot of really weird stuff in here. Okay? Now that might seem foreign to you, but actually let me give you a reason why people would think in terms of this. You can calculate the electromagnetic interaction between, say, two protons through a QED process where you exchange a photon, right? And what's interesting is that you get pretty much the right answer just using that diagram. okay, for the scattering amplitude of 2 protons. However, the exact same argument should apply that we applied here. I mean, the protons are really 3 quarks. Which of those quarks are exchanging the photon? These quarks can be emitting virtual photons that are creating virtual pairs. All of the same complications could be there. Okay? So there's really no reason why this would not get screwed up in the same way that this gets screwed up. However, there's a symmetry that is obvious here, and that is that no matter what happens in all of this complicated mess, the total electric charge is conserved. And if you're doing a long-distance scattering experiment where you just see the protons and you don't really resolve that they're made of quarks, all you care about is the total charge, and that's being conserved. The problem here is there's not really a conservation of of flavor in the same way that there's a conservation principle protecting this amplitude. Okay? All right, so my last example is not quite a true decay, but it's going to give us a very interesting result. And this is going to be the pion decay. So the pion decaying into a lepton plus some lepton neutrino. And remember, a pion is a bound state of an anti-up and a down quark. So we can write this as actually a scattering process. So that's the pi minus. I'm going to work with pi minus. And then we're just going to have a W that gets created when these 2 things annihilate. And then out of that, we're going to have an anti-lepton neutrino and a lepton come out. Okay? So, now, I'm calculating the decay of a bound state. The previous 2, okay, so yes, the quarks were a bound state in the proton calculation, but in this calculation, we've actually got the 2 quarks themselves, which are annihilating to form the W. So there's a part of the inside guts of what's going on that we simply can't ignore. And the truth is that if we wanted to calculate this process with this diagram, and this is the exact diagram. It's not like what I drew before with the protons and the neutrons where I said, I really don't know which one it's coupling to. This is still very hard to evaluate because these are bound to each other. And therefore, the energetics of that initial system is not just 2 free particles. There's some ground state wave function describing the bound state that they're in. So there's a lot more information that I would actually have to work with to accurately calculate this. However, and this is common in these experimental situations, we can extract something useful even though we don't know everything. So consider modeling this in the following form. Let's take a pion, come in, and then put a bubble of ignorance. And out of the bubble of ignorance emerges a W, and then out of that W emerges a lepton and an anti-lepton neutrino. Okay. And then what we're going to do is we're going to argue that the amplitude for this process, if we just start applying the Feynman rules to it, we're going to get a lot of this that looks exactly the same as what we've calculated before. But this time we're going to put in a quantity, F mu, which encodes our ignorance about this part right here. Yeah, Matt.
Should that be a lower mu? All right.
No, that should be an upper mu because I want it to contract with the lower and the gamma. One is up and one is down. It doesn't matter which. Yeah. Okay. So there's something happening here that we're claiming we don't know. We actually know it has to be described by an F mu, because if we just use the Feynman rules to evaluate the rest of this diagram, we end up with one uncontracted spacetime index. And so this factor of our ignorance has got to contract with that to make an overall scalar. So it turns out it has to be vectorial in nature. And we can ask, what could this F mu possibly depend on? Like, what vectors are there in this process that this could possibly depend on? Now notice this bubble of ignorance is before you've created these two things. You literally just have something going to the right, something weird happens, and then you have something going to the right. So what spacetime vectors do we have associated with this bubble of ignorance? Yeah, the only vector that's associated with it is the momentum of what's coming in. So we can immediately deduce that F mu has got to be proportional to the incoming momentum. And I'm just going to call that proportionality constant F pi, where you might call this the form factor of the pion. Form factors are just these general labels for bubbles of ignorance, and we're going to talk about pion decay, so this would be the form factor for the pion. I could pick a different particle and it would have a different form factor. Okay? Now, this thing is a scalar. Well, it has to depend on something that's in the picture.
True.
What scalars are in the picture? Like, what numbers are in this process? No, it has to be a dynamical number. It has to be something that... Say again?
I said mass, but I just guessed the energy.
The mass of the pion. It is literally the only scalar that's in this part of the process. It's the mass of the pion. Okay? So Fp... So Fp is a scalar, and the only thing that it can depend on is the mass of the pion. But at the end of the day, we've learned something interesting. This is our ignorance, F mu, but the only thing our ignorance can depend on is the mass of the particle coming in, that's the pion, and the momentum that it carries. What that means is that it doesn't matter what lepton this is and what neutrino this is. I could have an electron and an electron neutrino, or a muon and a muon neutrino. This factor F mu is going to be the same in both cases because it doesn't care about the lepton. It only cares about the pion. Now, go ahead.
Do the lepton and the electron neutrino have to be the same type?
Yeah. They have to be the same type. Now, why is that useful? Well, it's useful because although we can't maybe calculate the rate at which this pion decays into an electron and an anti-electron neutrino, we can calculate the ratio of how often it decays into electrons versus how often it decays into muons, because the ratio is going to have this same factor which will cancel out. Okay? So, yeah, in the interest of time, I'm going to skip to the bottom here. So if I calculate the decay rate into either channel, I'm going to have this F pi factor squared over pi, my notes are horribly written, h bar m of mass of the pion. And there are some steps filled in the notes, but they're not going to be very insightful. You can go look at it if you want. Times the mass of the lepton squared times the mass of the pion squared minus the mass of the lepton squared, quantity squared. Okay? So this is gamma. This is the decay rate for it to decay into a particular lepton. Okay? So then what we can do is just form the ratio. So we can take the ratio of the decay into the electron channel versus the decay into the muon channel. And the good news is that this whole piece cancels. Okay? Because it's the same for both of these. So it's really just this combination of mass factors that's going to determine the final result. And if you plug in the numbers, you find a result that looks like this. Joe Bales.
Just to clarify real quick, F pi is not mass, pion mass, it's like.
It's a scalar built out of the pion mass.
Okay,
So, I mean, you'd have to look at what the dimensions of this thing need to be
gotcha.
based on the dimensions of this. So does it need to be dimensionless? Does it have to have dimensions of energy? Does it have to have dimensions of length or whatever? And then you could take these two numbers and you could tease out. You throw in factors of C, obviously, because C is what you always use to fix up the dimensions.
Gotcha.
Okay. But at the end of the day, this is the ratio that we find. Okay? Pick a victim. Emily.
What's up?
Let's end this with a bang.
I feel like if I'm answering, it's going to be more of a winter, but
Why is that surprising?
because we see electrons more.
Well, no, this is what we see. This is the right answer, and it's what we see. Jacob so wants to be your friend.
Go for it.
Because the mass of the electron is a lot smaller, so shouldn't we expect those events more frequently?
Exactly. Kinematically, we would expect the pion to decay into the electron channel versus the muon channel more frequently because there's a bigger mass difference. If you're decaying, so we talked about this when we first started looking at decays. We said that one of the driving factors behind decay rates is, or a process in general, is the amount of phase space that you're going to have to play with. So if the mass difference between the pion and the electron is huge, that means you've got a lot of extra energy that you can distribute in the form of momentum. But if the mass difference is small, you've only got a little bit of energy left over to distribute, so you have fewer ways to do it. So just in terms of sort of phase space size, we would expect this to be a lot more common than this, but the calculation seems to be saying otherwise. Oh man. Who was going to get to do it? Brooks.
Yes.
I would do 5 cards to get to you.
I'm on.
Can you explain why this would be the case? Any guesses? Any guesses?
Can't.
First of all, does everyone understand the problem, the contradiction?
Yes.
I can repeat it if you don't. Okay, Brooks. Jacob still wants to be your friend.
I'll phone a friend.
All right, Jacob.
Does it have to do with the masses of the neutrinos associated with them?
Yep. Good guess.
Is this what we actually see?
That's what we see. Joe Bales.
Does it have to do with the massive boson having to carry a different amount of momentum? No, I guess it wouldn't.
All right, there's no way you're going to get it. No one's going to. I mean, I'm just going to explain it to you. It's like, it's mean to even ask this. This is hard, okay? So just very quickly, this doesn't take long. So first of all, let's just think for a moment. The pi minus is a spin 0 particle. It has no net spin. So that means that when it decays, the two things that come out have to have their spins anti-aligned. Okay? But of course, this is effectively a two-body decay. So if the pion's at rest, these things also come out with back-to-back momentum. Okay? So if I draw the process, if there's my pion and it decays, I'm going to have something shoot out to the right with a momentum p, something shoot out to the left with an equal and opposite momentum. If this is the lepton, and this is the neutrino, the antineutrino, then it turns out that the spin of this has to be to the right. Because one of the things that we talked about very early on with the weak interactions is that, well, first of all, it's just an observation that the weak interactions always produce right-handed antineutrinos. When we look out in the universe, we only see right-handed antineutrinos and left-handed neutrinos. So for this to be right-handed, I need the spin to point in the direction of the momentum. Okay? That's also just a consequence of the weak interaction vertex itself. But then what does that tell me about the spin of the lepton?
It has to be the other way.
It has to be to the other direction. Okay? So this is something that I know I need, and I can conclude from it this, based on the fact that this is at rest and it spins 0. Here's the interesting thing, okay? And it's hard to buy, but it's the reason this is happening. The electron, so by the way, what's the handedness of this particle?
No, right.
Yeah, this is right-handed, so both of these are right-handed.
Because they're spinning along the direction.
Okay?
He's laughing. It's good.
The electron is almost massless.
Okay.
And because it's almost massless, to leading order, the weak interactions are going to produce it as if it were massless. Which means that the weak interactions are going to produce it only in left-handed states. Because the weak interactions produce left-handed massless matter and right-handed massless antimatter. The muon, on the other hand, is very massive. And so the weak interactions are happy to produce right-handed muons because there's no suppression, because they're almost massless. So that story doesn't sound very convincing, but if you actually dig into the details of the amplitude calculation, you'll see it emerge. Okay, so the bottom line to this is to actually calculate results, okay, you can't just rely on the really simple basic arguments that we've used in the past, like, oh, the bigger the mass difference, the more prevalent it's going to be, because there's a lot of other subtle factors that are at play. And these can often change the results such that it's completely counterintuitive. Nathan?
You mean that taus, or is it a higher rate? Or?
So no, because once you get far enough away from 0, tau and mu are competing based on their masses. So it's more tied to the fact that the electron is very close to 0 than it is that their mass difference is some. So the difference between the mu and the tau, yes, the mu is a little closer to 0, but it's nowhere near 0, so it's not going to get this suppression.
Yeah, okay.
Spencer?
Is this where we get the concept of forbidden decay?
Forbidden decay? I wouldn't necessarily, well, I don't know exactly what you mean by forbidden decay, but I mean, my simple notion of forbidden decay is there's some rule, some symmetry conservation principle which says you can't do this. Like, you know, I can't have an electron plus an electron scatter into, you know, an anti-electron and an anti-electron because it violates. Or sorry, I can't have a neutron decay into 2 protons. I don't know, there's some, you know, those would be forbidden. There's probably other, so this is not forbidden, this is suppressed. And those are 2 different concepts. Forbidden is something is literally keeping this from ever happening, period. This happens, it's just suppressed. It doesn't happen very often. And there are other rules that you can get out of carefully studying the Feynman rules for these various processes and see other suppression factors as well. Okay, all right, that's it for today. Come back on Tuesday. We're going to have a homework quiz, and then we're going to talk about renormalization.
So you're talking about